Hello everyone, my name is Ching-Wen. I'm a PhD student from National Taiwan University. Today I will introduce our work. Force feedback from damp oscillation is a common effect in our daily lives, especially when shaking an elastic object or a container with liquid, such as swirling a glass of wine or casting with a fishing pole. For damp oscillation, when external force makes a system oscillate, the energy from the external force decreases and the amplitude of the oscillation decays correspondingly. However, such system could be complicated when external forces consecutively or even irregularly apply to it. Therefore, to simulate force feedback for damp oscillation, complicated physical variations and collisions from center of mass change, inertia and reaction forces, swinging of objects, and collisions from contained liquid or objects make it challenging. There are two categories of force feedback devices: active and dynamic passive haptic feedback, also called DPHF devices, could simulate such force. Active devices use propellers or motors to simulate the moving object or weight shifting of liquid, as in aeroplane and switch. However, delay in actuating motors or propellers is the limitation for simulating quickly change and complicated oscillation force feedback. DPHF devices use motors to present 2D shape change illusion as in transcaliber, or provide multi-level resistive and inertia forces as in drag-on. However, these devices focus on the weight change of rigid objects instead of liquid and elastic objects. The delay for moving the weights in these devices also limits the realism for quickly change oscillation force. In previous oscillation methods, travel via leverage travel effect, gravity cup controls fluid, balloon may produce asymmetric acceleration, and reactive grip generate torque feedback to provide force feedback for oscillation. However, these methods generally provide partial force feedback of oscillation, and most of them still have limited force feedback dimension or the delay issue. To provide 3D multi-level oscillation force feedback is still challenging. To render realistic force feedback for damp oscillation to enhance VR experiences, some design considerations are needed to be taken into account. For realism, users should perceive the proper resultant force as mentioned above, with the force net changing continuously corresponding to the hand movement. For oscillation directions, the method should provide force feedback for oscillation in different directions corresponding to the shaking movement in VR applications, such as shaking a bottle of water in 1D, swirling a glass of wine in 2D. The method should render different oscillation levels for the same task, such as shaking a bottle with different amounts of water to achieve VR versatility. For mobility, to allow users to freely explore VR scenes, mobility of VR devices is essential. Therefore, the size and weight of the proposed device should allow users to easily hold, shake, and perceive the force feedback. Inspired by elastic VR and elastic impact, which control elastic band length and extension distance to provide multi-level resistive force and impact. We propose ElastOscillation to control elastic band's elasticity to restrain the movement of the proxy, and 3D multi-level force feedback for damp oscillation to enhance VR realism. Here is the structure of the ElastOscillation. The 6 elastic bands are connected between a proxy and 6 DC motors in 6 directions of the 3 axes. The proxy consists of small magnet balls, and each elastic band is connected to a winding axle of the corresponding motor. The motors are affixed to a 3D printed frame with 6 motor cases on the controller. The whole device is affixed to a HTC Vive controller, a 3D printed small hook is used to affix the wires to prevent from interfering users. By extending and releasing the bands in pairs of the corresponding axes using the motors, ElastOscillation restricts the proxy movement at different range or levels due to different elasticity. When shaking ElastOscillation, the users perceive 3D force feedback of oscillation at different levels from the controller. The higher elastic force levels make the proxy difficult to bounce and restrict its movement to a smaller range. So the lower force levels for damp oscillation is produced, and vice versa. The axes on the ElastOscillation controller are the same as the axes of the Vive controller in Unity VR scene. We observe and categorize users' shaking movement into two types, 1D and 2D movement. 1D movement represents that the users shake the device back and forth roughly along an axis. Here is the proxy trajectory relative to the controller in 1D movement, using from Vicon shaking system. It looks like a strip or a cylinder. 2D movement represents that users shake the device roughly around an axis on a plane. And the proxy trajectory relative to the controller looks like a disc or a circle in 2D movement. To understand users' force level distinguishability for damp oscillation, we performed a force perception study. We conducted a pilot study to decide 3 distinguishable levels in 1D and 2D movements, respectively. Then, we used force sensor to measure the elastic force for these levels to further define oscillation force levels. Level 1 has the smallest range of movement with the weakest oscillation force, and vice versa. 12 participants were recruited to map oscillation force generated from our device to visual object size in VR in each task. Total 6 tasks were in 1D and 2D movement, and 3 levels were in each task. Participants were asked to map the larger oscillation force level to the larger object size. 3 repetitions were in each task. So, a total of 54 trials were examined by each participant. In X, Y, and XZ task, a ball hung from a fishing pole in the VR scenes could only be moved in a left-right tunnel, up-down tunnel, and on a floor-like plane, respectively. The participants could shake the device in these tasks to perceive the oscillation force feedback and adjust the ball scale to match the force feedback. In YZ task, a cube was in a pen-like object. By flipping the cube in YZ plane, they could adjust the cube size for the best matching scale. In Z and XY task, the participants shook the bottle along the axis and swirl the glass on XY plane, then adjust a liquid amount by percentage of full containers to match the perceived oscillation force feedback. The results show that significant differences are revealed among all pairs in XY plane, while for the other tasks, the significant effects are only shown between level 1 free and level 2 free. Therefore, users could clearly distinguish 3 levels in XY plane, and in other conditions, they could just distinguish 2 levels. To further observe how the oscillation force from our device affects users' VR experiences and whether the proposed force feedback enhances VR realism, we performed this VR experience study. These were 4 VR applications experienced in this study, including pen flipping for YZ movement, bartender style shaking for Z movement, wine-swirling for XY movement, and fishing for XZ and YZ movement. Based on the result of the force perception study, 3 force levels were provided in the wine-swirling and 2 force levels were in the other applications. 12 participants were recruited for this study. In each application, 3 haptic feedback methods were compared: fixed proxy as a baseline, non-elastic oscillation, and ElastOscillation for 2 oscillation types with and without elasticity. Here are the results in subjective 7-point Lakers scale. No significant difference is found in pen flipping. Notably, the score of non-elastic method is the highest. Some participants comment that the pen oscillation caused by the falling foot should not have such elastic or bouncing sensation, so non-elastic methods without such force feedback was preferred. Therefore, we suppose that the proposed feedback is not proper to simulate such rigid object collision type scenarios, and that's why the result of pen flipping has no significant difference. For bartender-style shaking and wine-swirling, most participants mentioned feedback from the proposed elastic method for liquid movement and collision simulation was much more realistic. They could differentiate force feedback levels more easily from the elastic method, since the proxy movement range became larger when the elastic bands extended. For fishing, almost all participants supposed that feedback from the elastic method was significantly more realistic and distinguishable. Some of them mentioned that they could clearly feel the fishing rod was elastic and bent when the fish hung onto the hook in the elastic method. Based on the results, we understand that oscillation force from our device is more proper to be used as feedback for shaking elastic object or a container with liquid. Furthermore, the scenarios requiring larger movement are more appropriate for our device, such as fishing. Therefore, in proper scenarios, force feedback from the ElastOscillation device significantly enhance VR experiences. The proposed method still has some limitations. The weight of the device is still a bit heavy. This is because we print extra frame to attach the motors to 3 axes. If the future VR controller is manufactured with the frame, it could further reduce the weight. ElastOscillation does not provide oscillation force along an arbitrary axis, but it renders the oscillation along and around 3 axes in 1D and 2D movement, corresponding to the controller coordinate. However, this includes most shaking movements based on our observation. There are still delays for motors to switch to different force levels or types, since users share the device after level switch in most of our applications, and the level switching latency is quite short. Users did not report that they were affected by the latency. Furthermore, visual feedback could also be added to mitigate the issue. In addition, the proxy consisted of several magnetic balls, so we could further dynamically increase or reduce its weight to perform different oscillation force patterns in the future. In conclusion, we propose a handheld device, ElastOscillation, to provide 3D multi-level damp oscillation force to enhance VR experiences. We conducted a force perception study and obtained that the 3 oscillation force levels in XY plane and 2 levels in the other movement are distinguishable. A VR experience study was further performed to realize how oscillation force feedback affects users' VR experience. It further verified that compared with other methods, oscillation force feedback from the ElastOscillation device significantly enhanced VR realism in proper scenarios. Thanks for your attention.